Hi everyone, welcome back. Today we're going to be looking at maximum and minimum values. And this is going to start our journey into this new chapter where we're going to be implementing what we've learned about derivatives. And more specifically, we're going to be looking at what derivatives tell us in relation to these graphs that we've seen before. So, as we start looking at what we have on screen here, I want you to focus on the left-hand side. On the left-hand side of your screen, you're going to see a function f of x. And this function f of x, it's going to extend from negative infinity to positive infinity on the x-axis. However, you're going to see a few maximums, minimums, maybe a cusp in this graph. And what I want you to focus on here is that we're going to be able to extract these maximums or these minimum values for a given function. So as I start looking at my function, f of x on the left-hand side of the screen, what I want you to notice, again, is that we have this maximum value that is attained at this x value for a. We have a minimum value at this x value for b, and we have another maximum occurring at this x value for c. However, when we talk about the maximum and the minimum values, what we're doing is we're extracting the function outputs for those values. In other words, what is the y value at its maximum point or at its minimum point? And that's what we want to focus on. So in this particular graph on the left-hand side, we're going to say that this graph f of x has a local maximum at f of a. In other words, the outputs of the function at the value of a. Now, this is a local maximum because if we start looking at some interval around the a value, then given some interval around the a value, the output is going to be the maximum value within that given interval. So it doesn't have to be the largest value for the whole function, it just has to be the largest value for a given interval. Now, similarly, we're going to be able to do the same thing for b. We're going to see here that f of x has a local minimum at f of b. In other words, the output for this function at the x value for b, that is the local minimum. And again, as we start looking at this local minimum, if we were to build an interval around this value for b, then the outputs for that function would produce the smallest value of f of b within that interval. Now again, it doesn't have to be the most lowest point or the most minimal point, it just needs to be a minimal point within some interval. And that's what we call a local maximum or a local minimum in this case. And then we're going to look at the last one for that given function on the left-hand side of your screen. We're going to be looking at the very last function output that we can have here. And we're going to say f of x in this particular case has an absolute maximum at f of c. Now, why is this different? Well, first off, f of c is still producing a local maximum. However, to be a little bit more precise, f of c is actually the highest point of this function. It's the largest point, or it's the largest output that this function attains on its domain. Anytime that happens, you have an absolute extrema, meaning that you can either have an absolute maximum or an absolute minimum. In this particular case, it's an absolute maximum. Now, one of the items that you're also going to notice here, and we're going to go over to the right-hand side of the screen, where we now have this same function, f of x, but now I've restricted f of x to only exist on the interval from a to c. When f of x exists only on the interval from a to c, as we've defined it here, then one of the things that we then want to see, or we then want to extract, is going to be where are these maximums and minimums now occurring. And the way that we want to extract this is by identifying that we do have some type of maximum or some type of minimum for the given function inside of the interval from a to c. So what does this look like then? Well, we're going to see that the function f of x here has an absolute minimum at f of b. Now, why is it absolute this time? Well, it's absolute this time because we now restricted f of x onto an interval, and within that restriction of f of x on that interval, the output f of b is the smallest value that that function gives. Therefore, it's an absolute minimum. Now, do we have an absolute maximum? Which is the largest output in this given graph? Well, between f of a and f of c is higher. So f of x has an absolute maximum at f of c. And there we are. So we then get to see that we have a way to identify what is an absolute maximum, what is an absolute minimum, and having an absolute maximum or an absolute minimum doesn't mean that we're just restricted to an interval, because as we saw in the very first graph on the left-hand side of your screen, we actually were able to extract this absolute maximum where this function was unbounded or unrestricted for its domain. So again, that's awesome to see. Now, let's extract a little bit more. What are derivatives going to tell us here? Well, derivatives actually give us a really good insight into what is happening and how we find these maximums or these minimums. On the left-hand side, and on the right-hand side of the screen, I am building these tangent lines at f of b. So I would then ask, what is the slope of those tangent lines? Well, the slope of the tangent line is the derivative at x, or in this case, the derivative at b. So the derivative at b must be equal to 0. In other words, the slope for the function evaluated at the x value of b is equal to 0. That translates to calculus talk as f prime of b is equal to 0. Wow, that's amazing. So let's look at f of c. Well, once again, the slope for that tangent line is the same as the derivative of the function evaluated at c, and that slope of the tangent line must be equal to 0. Interesting. Okay. Well, there's one more that we then need to talk about, and that is f at a on the left-hand graph. So f of a, it does not have a slope of 0 because in this particular case, we have this sort of cusp taking place. Now, what's going to happen there, right? We then want to identify what's going to occur. Well, this is what happens. We have this vertical tangent line. This vertical tangent line would tell me that my derivative evaluated at a does not exist, or it's undefined. Now, this is very interesting because now we're able then to extract that if we have some maximums or if we have some minimums, then these derivatives are letting us know that we have some maximum or some minimum occurring at some given x value. All we have to do is identify what it is. Now, it's completely possible that this derivative could possibly deceive us. Now, you might be saying, well, Mr. Castro, how can math lie to you? Well, if you look at a function, say that we were looking at a function of x cubed. As we're going to see, x cubed will have a point or an x value where the derivative will be equal to 0. However, it is not classified as a maximum nor a minimum. And that's going to lead us into some interesting talks. But before we get into that, I want to define what an absolute maximum and absolute minimum, a local maximum and a local minimum are a little bit more concrete. So this is using a little bit more concrete definitions as to how we're looking at these absolute maximums, absolute minimums, local maximums, or local minimums. So we start off by saying let f be a function with a domain D. Then f has an absolute maximum value on the domain D at a point C if we get that all the values, all the function outputs are less than or equal to the function evaluated at that point. Now remember what I said, absolute maximum is the absolute maximum point on that graph. And this has to work for all of the x values on the domain for that function. Also, for the absolute minimum, so we can have an absolute minimum value on a domain D at a point C if all of your function outputs are greater than the function output for f of c. And this has to work for all of the x in the domain D. The local maximum and the local minimum values work the exact same way. A function f has a local maximum value at a point C within its domain D if f of x is less than or equal to f of c for all of the x in the domain D that has to lie on some open interval containing c. Okay, so again, a little bit more discrepancies there, but again, or more technicalities there, but again, essentially we're still looking at the exact same process. Local minimum. A function f has a local minimum value at a point C within its domain D if the function f of x is greater than or equal to the function output f of c, and this must be for the requirements that all x in the domain, except they have to be lying on some open interval that contains c. Awesome. So we're going to now go through and we're going to start developing more of a concept as to what it is to be this critical number that we're going to be looking for and how it is that we're going to be looking for it and using that critical number. So stick with me and we'll define it in just a bit. All right, so here's the definition for that critical number that we're going to be looking for, or these critical numbers that we're going to be looking for. We're going to want to identify a critical number of a function, and a critical number of function f is a number c in the domain of the function f such that the derivative evaluated at that value is equal to 0, or the derivative evaluated at c is going to be undefined. Now, again, this tells us that for this derivative, or for this function that will produce a derivative, we then need to identify what is this particular value. Is it going to cause this derivative to be 0, or is it going to cause it to be undefined? As soon as we find out those values, we're going to call them critical numbers. Once we find those critical numbers, all we have to do is test those numbers. So the very last item that I want to talk about before these examples is the extreme value theorem. Now, the extreme value theorem says that if f is continuous on a closed interval from a to b, then the function f attains an absolute maximum value, which we'll call f of c, and an absolute minimum value, which we'll call f of d, at some numbers c and d on a given closed interval a and b. So this goes back into that very first example, or that very first graph that we depicted on screen, and this is what we're showing on the top right hand corner of your screen, that if we were to restrict f of x into that closed interval from a to c, then we're guaranteed an absolute maximum and an absolute minimum. The only thing about absolute maximums and minimums is that it can occur at the endpoints. Typically, the endpoints don't have to be maximums or minimums. However, because we're restricting the function to some interval, we have to test them. So in order for us to be able to extract all this, let's work on this example. And I have this example here that we want to find the extrema of f of x is equal to 3x to the fourth minus 4x cubed on the interval from -1 to 2. Okay, so one of the first things that we're going to have to do is we're going to have to go with a critical number. So let's go through and let's find these critical numbers. All right, so here we go. We're going to take the derivative. So we're going to go with f prime of x. F prime of x in this case is going to get us 12x cubed minus 12x squared. Perfect. And so what we're going to do now is we're going to find the critical numbers by setting this function equal to 0. And again, we could either set the function equal to 0, or the derivative equal to 0, or try to find where the derivative is undefined. However, this derivative will never be undefined because the derivative is continuous on the real number line. In other words, it's continuous everywhere, therefore there's no discontinuities, meaning that there will not be a place where this function is undefined. So all we need to do then is set this function, this derivative of this function, equal to 0. Now, in doing so, I'm going to factor out a 12x squared because that's the GCF, which means I'm going to have x minus 1. And now I go through my algebra techniques and I find that 0 must be equal to 12x squared, or 0 must be equal to x minus 1. Well, this is now going to give me that x is 0, or x is going to be equal to 1. So we get these two different values, and these are the critical numbers that we're looking for. So these are your critical numbers. So critical numbers, yay. So we get x is equal to 0 and x is equal to 1. Awesome. So that's part of our answer in the whole process of finding this extrema. Now what we're going to do is we're going to test these critical values into the function. And I also want to test the endpoints for the given interval. Because at the end of the day, if we're finding the extrema, that means we're finding all of these absolute maximums and minimums that are occurring for this function on this given interval. And again, extreme value theorem tells us that they could possibly exist at the endpoints. So let's go through, and I'm going to order this on a table to make sure that I go through and I identify every single critical point and every single endpoint for this interval. All right, so here we go. We're going to insert some x values, all right, and then we're also going to evaluate those x values using the given function. Now, one of the first values that I want to evaluate is going to be the endpoint of -1. The other value that I want to evaluate, and I'll write these here, -1. The other value that I want to evaluate is a critical number of 0. The next value is going to be the critical number of 1. And the last value is going to be the endpoint of 2. So I want to evaluate these 4 values for this function. Let's move this a little bit more to the right. There we are. And so again, here I'm just going to identify that this is one of my endpoints. This is another endpoint all the way at the bottom. And these in here are my critical numbers. So now that we've identified this, let's go through and let's get those outputs. Okay, so we're going to substitute -1 into the function. So substituting in -1 into the function, that's going to be f of -1. So 3 times the value of -1 squared, that's going to be 3, minus 4 times -1, well, 4 times -1 to the power of 3, that's still going to be a negative, so negative times a negative is positive, and this is now going to be positive 4, which means 4 plus 3 is 7. I'm going to test f of 0, so substituting the value of 0 into my function, that's going to produce 3 times 0 minus 4 times 0, which gets us 0. F of 1 into my function, and that's going to get me 3 minus 4, which is -1. And finally, substituting in the last endpoint, f of 2. Substituting in this endpoint, 2 to the power of 4, that's going to be 16. 16 times 3 should get us 48. Then we're going to have 2 to the power of 3, which is going to be 8. And then 8 times 4 should get us 32. So 48 minus 32 should get us 16. There we are. All right, it's not looking too bad. Now, once we have all of these values, we then want to identify which value is the largest value and which value is the smallest value. Well, the largest value here, automatically 16. Smallest value is then going to be -1. So we get an absolute maximum and we get an absolute minimum. And that's what we're looking for when I specify that we want to find all extrema for this function, meaning that we want to find these absolute maximums or these absolute minimums. So let's specify this now. F of x attains an absolute maximum of 16, and this is when x is equal to 2, and an absolute minimum of -1, and this is when x is equal to 1. So we do get an absolute maximum and we do get an absolute minimum. And again, I want to state them at the very end explicitly like this to communicate to the reader that we have found this maximum and this minimum. All right. Now, what's really interesting about this is, remember that I said that you could possibly have a critical number that doesn't produce neither a maximum or a minimum. That number, or one of those numbers, actually appears here. The x value of 0 for this function does not produce a maximum nor a minimum. And that's interesting to see. All right, so I will give you a quick depiction of what that means and what that looks like in just a little bit. All right, so here's the depiction of that function. This is the function that we're given here, that we have as our function f of x, which is 3x to the fourth minus 4x cubed, bounded by the interval -1 to 2. And you're going to see here that we do have an absolute maximum. That absolute maximum is occurring exactly where we found it at 16, when x is equal to 2. So that was your absolute maximum. This function also attains a minimum value. We found that minimum value to be -1, and that's -1 whenever x was 1. And so that was our absolute minimum. Now remember, I said x is equal to 0 came out as a critical number. However, you're going to see here for this function f of x, at x is equal to 0, the function to the left of it is decreasing, and the function to the right is also decreasing at x is equal to 0. Which means this function is neither producing a maximum nor a minimum at x is equal to 0. Meaning it's not a point that will produce a maximum nor a minimum. So again, very interesting to see. It does happen on occasion, and we need to be prepared for when that happens. All right. Let's go ahead and let's focus on a different type of question now. Very similar, but a little bit more complex. So here goes your example. We want to find the extrema of the function, we're going to call this function g of x, which is going to be equal to 2 sine of x minus cosine of 2x on the interval from 0 to 2 pi. All right, so again, we have to go through the whole process once again. In order to find these critical numbers, we have to then take the derivative. So let's go through and let's take the derivative here. So finding g prime of x, taking the derivative of 2 sine of x will get us 2 cosine of x, plus, this is because the derivative of cosine of 2x will get us negative sine of x, so negative sine of x times this minus sign would get us a positive. And here we would get, by the chain rule, once we apply the chain rule, we would get 2 multiplied by cosine of 2x. All right, so this is our derivative. Oops, sorry, I put cosine. My apologies. 2 sine of 2x. There we are. Better. Great, so now we're going to go through and we're going to set this derivative equal to 0. That way we can find where our critical numbers are at. And again, just by setting the derivative equal to 0 doesn't mean we're going to find all of the critical numbers. Sometimes we have to set the denominator if the derivative has a denominator. And more specifically, if it has a variable in that denominator. So far we get this. Now we have to dip into our trigonometry bag of tools. And what we're going to do is we're going to try to see if we can manipulate this equation so that we can solve for x. So what I want here, I'm going to use a double angle for sine. That double angle for sine is going to be 2 sine of x multiplied by cosine of x. That's my double angle for cosine. So let's extract that. All right, so that's a double angle. Perfect. And the reason I want to do this is because using the double angle, I now have a common factor, otherwise known as my GCF, of 2 cosine of x. And I'm going to factor that out. So 2 cosine of x is now going to multiply the quantity of 1 plus 2 sine of x. And again, this whole product is now equal to 0. So what we're going to do is we're going to set each term here, or each factor, equal to 0. So we're going to set 0 is equal to 2 cosine of x, or 0 is equal to 1 plus 2 sine of x. What this gets us then is going to be that cosine of x must be 0. Well, at what angles within the interval from 0 to 2 pi does that happen? Well, at 90 degrees, in other words, pi halves, we get this to occur. And it also happens again at 3 pi halves. So we get 2 different values. We get pi halves and 3 pi halves that make cosine of x being equal to 0. Now for the second equation, we're going to get negative 1/2 is equal to sine of x. And again, all we did was we isolated sine of x. And now we have to go through the whole process and think about what angle measurements on the interval from 0 to 2 pi will give us a sine ratio of negative 1/2. Well, that is I'm going to walk through this with you all. And so I'm going to use a technique of identifying where sine of 1/2 occurs at what angle measurement, and then I'm going to use radians and trigonometry to extract the angle that I'm looking for. So sine of 1/2 is or that ratio occurs for a 30-degree measurement. So that's one thing that we can then extract. Sine of some angle or sine of 30 degrees will get us 1/2. Now I'm going to convert that into radians, which means sine of pi 6 is going to get us this 1/2 ratio. Now sine here, this ratio for sine is negative, which means by the logic that sine needs to be negative, that means my y values need to be negative, and they only occur in quadrants 3 and quadrant 4. So the reference angle of 30 degrees, or pi 6, must lie in the third or the fourth quadrant. Now, if I'm incrementing by 30 degrees, then on the third quadrant, I know that the negative x-axis, that's the angle measurement for pi, which means I'm going to add 30 degrees to that, or in other words, I'm going to add pi 6 to that to get me the 30-degree reference angle onto quadrant 3. So pi plus pi 6 should get me 7 pi 6. So I get a new answer of 7 pi 6. I also need a reference angle in quadrant 4, and I'm going to do the same thing, except I'm going to subtract by 30 degrees in order to get the reference angle of 30 degrees onto quadrant 4. In other words, 2 pi minus pi 6, well, 2 pi minus pi 6, that's going to be 11 pi 6, which means 11 pi 6 is my other value that I'm looking for. So these are the critical numbers that we found on that given interval. So again, critical numbers. These critical numbers are x is equal to pi halves, 7 pi 6, 3 pi halves, and 11 pi 6. So we found 4 critical numbers. We have to test all of them. And we not only have to test all of them, but because we're given this function g of x on this interval, we must also test the interval as well. So we have some work ahead of us. Let's see. Here we go. Okay, so I'm going to evaluate some x values, and I'm going to evaluate them using my function g of x. The values that I am identifying here, or evaluating, the first one is going to be my endpoint, 0, and then I'm going to go through and increase through the interval. So I have 0, then I'm going to have pi halves, then we're going to have 7 pi 6, then we're going to have 3 pi halves, then we're going to have 11 pi 6. So these are the 4 critical numbers, and then we're going to have the last endpoint, which is 2 pi. And so again, what we're looking at here is we're evaluating the endpoints. And again, the endpoint. And these are the 4 critical numbers that we found. All right, so let's go through and let's start evaluating these specific numbers. So the endpoint, first one, g of 0. So g of 0, we're going to make the substitution. We're going to get 2 times sine at 0 minus cosine. 2 times 0 will get us 0. Evaluating this, well, 2 sine of 0 is 0, but minus cosine at 0. Cosine at 0 is 1, and we're subtracting it, so this must be negative 1. Let's evaluate pi halves. This is 2 times sine of pi halves minus cosine. Cosine of 2x, but we're inserting pi halves, which means the 2 will cancel out with the half, which means it's just cosine at pi. Sine at pi halves is going to be 1, so that's going to be 1 times 2. Cosine at pi is -1, but we're subtracting, so this is 2 minus -1, which is going to be 3. All right, that's looking pretty good. Looking at the next one, 2 times sine of 7 pi 6 minus cosine at 7 pi thirds. Because remember, 7 pi 6 is going to be multiplied by 2 with the initial function, because we have cosine of 2x. So 2 times 7 pi 6 is really just 7 pi thirds. So we go through and evaluate this process here. So sine at 7 pi 6, that is -1/2. So that's pretty cool. So we get -1/2 here, and that's now going to be -1/2 multiplied by 2. And I'll write it this way, -1/2 multiplied by 2, minus cosine at 7 pi thirds. Now this one's going to be interesting a little bit because 7 pi thirds is already 1 full rotation around the unit circle. Because 1 full rotation around the unit circle would be 6 pi divided by 3. In other words, it would be 2 pi. 2 pi can be expressed as 6 pi divided by 3. So this is just one more rotation above, or sorry, one reference angle above that rotation from 0 to 2 pi, which means this is back in the first quadrant, and we're asking for cosine of 60 degrees here. All right, so interesting there. Cosine of 60 degrees, then, that's going to be 1/2. So now we get -1 minus 1/2. -1 minus 1/2 is going to be -3/2. Nice. Let's keep going. The next one is 2 times sine of 3 pi halves minus cosine of 3 pi. Remember, the 3 pi halves is going to be multiplied by 2, therefore we'll simplify 2 divided by 2. Okay, sine at 3 pi halves. Well, sine at 3 pi halves is going to be -1. So this is going to be 2 times -1. Cosine at 3 pi, that's back into a reference angle of cosine of pi, which is -1. Which means this is going to get us minus -1. So -2 plus 1 should get us -1. Finally, 11 pi 6. So this is sine 2 times sine of 11 pi 6 minus cosine, remember 2 times that argument, which will be 11 pi thirds. I'll let you work on this one, so please put pause on the video, work it out. Try to work this out without a calculator. Try to rely on your unit circle. So put pause and give that a shot. When you come back, both of these last two are going to be done. So again, please put pause on the video now. So here we are. The last two values give us a value of -3/2 and a value of -1. And so again, since we're wanting to find these extrema on this interval for this function, we then just have to identify which values are the largest produced on these intervals and which ones are the smallest. Well, so far we have a largest value of 3. Okay, so that's a biggest value there. Smallest value, in other words, smallest meaning on the y-axis, the furthest away from y is equal to 0. The value is not -1, but instead it's going to be -3/2 because this is going to be -1.5. So here we found that we do have an absolute maximum and we do have absolute minimums. neither of these occur at the endpoints. Interesting to see, but let's write it up. So g of x attains an absolute maximum of 3, and this is when x is equal to pi halves. And an absolute minimum of -3/2 when x is equal to 11 pi 6, or let's go with the first one, 7 pi 6, and x is equal to 11 pi 6. Great. Now, let's show a graphical representation of this. That way we can definitely see that we hit these on the mark. All right, so here's the graph that we're looking at when we're looking at the function g of x. Here we go. So this function is the function of g of x that we're initially looking at. Now, before I move on, let me box my answer here. This is the answer that I'm looking for. Now, here we can definitely see that on this bounded interval for g of x, we clearly see this maximum here, and it's definitely an absolute maximum. And the absolute maximum occurs at pi halves, and it's a value of 3. That's exactly what we wrote down. G of x attains an absolute maximum of 3 when x is equal to pi halves. Awesome. We also see that this function attains a minimum, and it's the absolute minimum on this given interval. It attains it at 2 different spots. This absolute minimum is attained at 7 pi 6 and 11 pi 6, and that absolute minimum is -3/2. And that's exactly what we wrote. We said that an absolute minimum, g of x was going to have an absolute minimum of -3/2 when x is equal to 7 pi halves and when x is equal to 11 pi halves. So again, there's no need to look at the actual functions if we wanted to extract these absolute maximums and minimums. All we have to do is calculate or find what are these critical numbers, as well as testing the endpoints, evaluating all of that at the endpoints for the function, evaluating the endpoints and the critical numbers at the function itself, and then from there extracting what are those values, which ones are maximums, which ones are minimums. So I hope that you all enjoyed this lesson. Stick around, and we will be talking about the mean value theorem in the next section. So stay tuned for that, and I will see you next time.